Uh, Welcome to the recommendation system part 2, non-personalized recommendation systems. In this session, we are going to cover the important topics such as the cold start problem, how we are going to address the non-personalized recommendations. There are various techniques which are broadly classified into aggregated opinion recommenders and product association recommendations or recommender systems. Okay, so the purpose of a recommendation engine, as we know, is to filter out irrelevant content and give you a meaningful information or a relevant information, right? It is as good as asking a question and giving an answer, but here the only twist is you will not be asking any question, rather it will give you directly an answer which is nothing but a recommendation or suggestion on what you want or what you like. It's as good as telling you that this is what you like, so we are suggesting you this. So with that as a purpose of recommendation engine, there is a basic problem that we need to address. What you see in the screen is a car covered with snow. So we all would have faced this situation in our life if you are using a four-wheeler or two-wheeler. Sometimes if you leave it for a long time, if you leave it idle for a long time, you will find it difficult to start, right? What we call colloquially as starting trouble. Here, imagine this car is equivalent to a website which you are trying to browse, and the battery inside the car, which is actually required to start the car, is a recommendation engine. Now, when you try to start the car at this instance, it will not start because of the cold battery, which is why it is called a cold start problem. It will take some time to actually get started. It actually needs to warm up and get started. Similarly, if I equate the battery engine to a recommender system, the recommender system has to get some input to actually show right recommendations. Input could be either what you like or what you watch or what you share. It could be implicit, it could be explicit. But since at the beginning the recommender engine won't have any inputs from you, it will get into a situation which is similar to cold start. Now, mechanically, the cold start problem is not yet addressed. We still have to actually keep igniting our engine to get it started. But in case of recommendation engines, we have actually solved this problem by means of non-personal recommendations. So this is the key here, non-personal recommendations. So what do we mean by non-personal recommendations? Actually, we would all love to get a personal recommendation, right? Which is customized to us, like based on your characteristics, based on what you like. If somebody tells this is what you want, and if it is suiting our needs, we would be very happy and delighted. But when the system doesn't even know anything about you, right? What you look like, what you know, what you feel, what you buy, what you like, it still wants to give you certain feedback so that you feel that you can go ahead and purchase it, like it or dislike it. It could be it could go anywhere, but mostly the recommendation engines would want to give you a right products or recommend you the right system. So the non-personal recommendations typically come into the picture when you as a person log into any site at the first moment or at the first instance, or when the system is completely unaware of you. Now, what are the characteristics of non-personal recommenders in general? It doesn't rely on user preferences. For instance, if you are going to a shopping site, right, you may be preferring a certain color, or you may be liking a certain brand, or you may be preferring certain size. but the system will not know any of these informations. So the non-personal recommendation engine will not rely on any of your user preferences. It will not have any information about your behavioral patterns. Since this is the first time that user has logged into a site, right, or user has walked into a store for the first time, the system will not know actually historically the purchases that you have made, because there is no such historical patterns that we have given as an input to the system. And in terms of attributes, right, every product has got certain attributes. For instance, if you are logging into a Netflix or Amazon Prime to watch movies, each movie has got its own attributes, such as the genre, the director, the hero, right, or the casting, music director. These are all certain attributes for a movies. The system doesn't know the attributes of the products that you like, right, because it doesn't even have an information of what products you would like. So without any of this information, it still goes and gives you certain recommendations which it feels that will satisfy your needs or will suit the needs of you. That's the specialty about non-personalized recommendations. I hope it's clear. The recommendation techniques in general are classified into or categorized into personal and non-personal recommendations. And we will not deal with personal recommendation because the item of interest and for this session is non-personal recommendations. And non-personal recommendations are broadly classified into aggregated opinion approach and product association recommendations or recommenders. So we will go in detail about these two areas of interest, which are non-personal recommendations. Stop me at any point of time if you have any questions. Okay. Okay, what I show you here is aggregated opinion recommender examples. So first, we are going to deal with aggregated opinion recommenders. So what are the general examples that we see which are part of aggregated opinions? So we told that the system doesn't know anything about you, correct? But still, there are certain things which you might like, because we humans as a social animal have certain characteristics which could be part of the social groups, right? So for instance, you may like a movie which could be a most popular movie, or you may pick up a dress which is mostly recommended by your favorite celebrities, right? Or you may watch a cricket match because your favorite players are watching or playing the match. So there are certain items inherent to us in terms of our behaviors that is being used or harnessed by the recommendation engines to recommend you any specific product or service. For instance, if you log into a Twitter, or if you log into a Facebook, or even if you go to Google, you might have seen or encountered this term, the trending. So what exactly is the trending? It will actually tell you worldwide or your country specific or your localized or your local specific, what are the items, products, or the news which is trending, which will catch your attention. For instance, if there is any specific product, or if there is any specific movie which is trending today, you might like to go and watch, right? So similarly, how is this trending items, how is this trending movie or trending item being decided? It's based on an aggregated opinion from all the users. Say a new movie is released, people go watch the movies. It may not be you, it may be different people across different genders or different locations, go watch, rate the movie. Based on that, if everybody has rated good, probably that could be the one which is trending, and that will be displayed as a trending result. So what is the motive behind it? If something is trending, probably we might like it because it's the most popular one, so we go ahead and watch. So that's the funda behind trending. Now almost all social media sites has, or even shopping carts has incorporated what is actually trending. And the other one is popularity based. It's again a part of our behavior. Whatever is most popular, you may or may not like it, but still the recommendation engines would compute the popularity based on the user inputs as to what you can actually watch or what you can buy. So here I have listed the top 20 watched movies in US for quarter 2. So let's say you log into Netflix to watch a movie. You don't know what movie to watch, right? But the moment you see that these are the top 20 watched movies in US, then you might get a feeling that, okay, so since these are the top 20 watched movies, probably this could be good. Probably since people have liked it, I may also like. So this is another aggregated opinion recommender where based on the input of users, it actually comes and it actually derives the popularity and recommends you that. And other one is editor's pick, right? Editor's pick is something which has been traditionally there in the marketing world, wherein if you go and watch any advertisements, right, your favorite celebrity might come and actually advertise your product. The reason behind is once you establish a connect with someone, you may actually like the product or service that they recommend. Similarly, if you feel that somebody is very famous or somebody has a deep knowledge in a specific field, and if he or she is recommending a product or a service, then it's highly likely that it might be a good product. So you might start exploring the product, or you may go ahead and buy that product. So that is the category of editor's pick, wherein even if the engine doesn't know anything about you, it might still recommend based on the most favorite from the editor's point of view, or the favorite from the particular celebrity's point of view. So those are editor's pick. So I hope we are clear about aggregated opinion recommenders. So if you think that just computing the feedback from all the users and then display it in terms of either popularity based or trending or editor's pick is easy, it is definitely not easy, because there are a lot of things which happens in the background to actually rate a certain item as a popular one or a trending one. Okay, so we will be looking into certain algorithms which actually helps derive these specific recommendations in the forthcoming slides. Okay. Now coming, this is an interesting portion wherein we are going to deal with one of the algorithms which actually helps in telling you the most popular item, right? So the algorithm that we are going to deal with is damped mean recommender system. It is a very famous algorithm, very simple and a famous one, easy to start with, to actually give you a good recommendation. So it's as good as giving you a statistical summary. If you're able to understand a little bit of math, we will be able to get it. So what we will be doing as a part of this algorithm is I will be switching back and forth between slide and Excel, wherein I will be walking you through how the steps of algorithm will look like, and I will also show you a code demo that we have implemented for a movie set that will recommend you the most popular movies based on the ratings of the users. Okay, so let me quickly show you the data set. So what we are going to do as a part of this algorithm is we have actually picked up different movies watched in a different period of time, and each movie is given a specific rating by users who have watched that movie, and each movie is identified a specific movie ID, and a user who has watched that movie is also identified by a specific user ID. So what you see here is a list of all the user IDs, movie IDs, and the ratings and the corresponding timestamp combination. It's a simple table which tells you what is the corresponding rating of a movie by a specific user. Remember, each user may rate the same movie differently, right? So that's about a simple data set. So what we are going to do is, what is the most popular movie based on this recommendation, based on the ratings of the users, right? So for that, okay, I hope we all are a brief idea about averages, right? Which we use, which we might be using day in and day out. I'm just showing you a simple table. If you can, for you to visualize and understand this algorithm better, right? Let's say there are three movies with IDs 1, 2, and 3. These are three different user IDs, and sorry, these are three different user IDs, and these are three different movies. Sorry, and these are the ratings provided by different users for this specific movie. Okay, let us say user 1 has given a rating of 2, user 2 has given a rating of 4, user 3 has given a rating 5, and user 4 has given a rating 6. All right, okay, imagine that rating is in the scale of 1 to 6, or we can set it up between 1 to 5 also, but here I have picked up between 1 and 6. Okay, so a simple average of the rating can be computed. This is a simple average, right? Just sum of this divided by total number of users who have rated. There are 4 users who have rated this movie, so the average rating for this movie is 4.25. As simple as that, right? But the problem comes only when you see that not all the movies are watched by the same number of users, right? Let us say wherever I have given 0, it means that the particular user has not rated this movie or not watched this movie. So if you see a movie ID 3, it has got only one user who has rated it as 5. Movie ID 2 has got 3 users who have given ratings, but movie 1 has got 4 different users. Now if I say take a simple average, does it give me a relevant result? For instance, the movie is 1, so watched by 4 different people, which I assume that the movie could be popular compared to the 2 and 3 because it has been watched by 4 people. And it is given a 4.25 rating average, and movie 2 has got only 1.33 average, and movie 3 has got 5 average, since because only one person has watched and has given a rating of 5. So if I just have to go by the most popular movie in these three by simple average, I might just pick it up movie 3, right, and say, oh hey, see, this movie has got a rating 5, so you should go ahead and recommend. But there is a catch, because the movie is watched only by one user, whereas movie 1 is watched by 4 users. So obviously you need to take into consideration the number of users who have actually watched the movie, and based on that, actually we should normalize these averages. Otherwise the average is going to give you a different result. Okay, so coming back to the slide, a stereotyped recommender system, a stereotyped or a simple recommender system will actually take average of all the products, average of all the ratings, and might give you recommend you the most popular movie based on the highest average, which would actually cause you this specific problem, wherein a movie, even though it is not watched by all, but still might get a highest rating. So we need to actually moderate this, or we need to actually bring it to a same scale. So in order to do that, there is a variant which is being introduced, which is called as a damped mean recommender system. So instead of a stereotyped recommender system, we are going to get into a damped mean recommender system. Now, what is a damped mean recommender system? A damped mean recommender system actually takes into consideration even the number of users who have watched that movie. So what is the assumption that the damped mean recommender system makes is it actually thinks, it actually gives an average rating for all the movies at the first instance, and based on the number of users the ratings will keep increasing. So what it means basically is, let us say the average rating for any movie at the beginning is 2.5. It is a number which is decided arbitrarily, and k is another term which is u here. Sorry, it's the global mean rating. So it's another term which is decided, for instance, pi. It is number that you can set it up however you want. So what we will have to do is we have to damp the mean. So what are the steps involved in damping this specific mean is, you take the same data set, right? What you do is you count the ratings of all the movies. You arrive at the count as a step one. Then what you do is we have to apply this formula, which is nothing but summation of this count of all the ratings plus alpha into u. Alpha is nothing but the strength of evidence that we need to overcome the global mean. This number is actually decided based on the specific problems. So here we have picked up this specific number as 5, and also a specific average that you can take. It's a common average that you can use, which is H6, which we have arrived over here. So I have picked up this specific rating, which has come out of simple recommender system. And if you see, I have calculated the numerator over here, which is H11 this plus 5 into H6. Similarly, we do this for all the 3 different movie IDs. Then what we do is, here is a count. Count is nothing but the number of users who have actually given the rating. So here it is 4 users, here there are 3 users, here there is only 1 user, and you add that to the count that we have decided, which is this alpha u value here, and nu what we have decided here is 5. So this count gets added over here, and finally we compute the mean based on the formula, that is rating plus alpha into nu divided by the global u plus alpha. So what happens is, once you do this, right, you get a different mean, and you can actually compare the averages over here, right? We call it as a damped mean. The reason being, we are damping it. When you apply a damp, it is actually as good as applying an opposite pressure, so that you don't bring in, you reduce the variance among the averages, right? Now if you see, it's all almost in the same scale. Movie ID 3 has got a rating of 3.44, a movie ID 1 has got a rating of 3.85, right, which is different from whatever is the rating that we have got here. Let me look for questions. Okay.
I have
Yeah,
one question.
Yes, please go ahead.
Yeah, just
Are
go
you
to
able to hear
Excel
me?
sheet. Yeah, I can hear you. Can you hear me?
Yes, I can hear. Yeah.
Yeah, can you just go to the Excel sheet?
Okay.
So if you look at H13, should that not be 5?
1 minute. No, this is the summation of the ratings that we have got.
Yeah, exactly. So I'm talking about H13. I didn't say H12.
Oh, sorry.
Because if you
Oh,
look
what is
at
it? Oh, okay, sorry. Correct. I apologize, it's a typo. So it's a 5, that's correct. Is it right? Uh, so, hello?
Hey, I have a question. So, can you hear me?
Yes, may I know who this is?
Yeah, this is Kanan here.
Okay, hi,
So,
Kannan.
can you please help me in understanding why we took that user count as 5 over here?
It's actually specific to any domain. Right, you are free to actually use the user count here how much ever you want. For this specific problem, I took 5, but sometimes what would happen is, let us say you have around 10 different rating scales, okay, 1 to 10. At that point of time, you might actually pick up a user count as 10. So here, for this specific problem, I picked it up a user count as 5. It's an arbitrary number that you can actually decide.
Yeah, can you
So
give an example where I can actually choose a different number? Maybe some other real-time example which can help me to understand what could be the arbitrary value for some different use cases?
um, so what would happen in general, the recommended value for you to use is 5, provided the user set count is less than 10. Okay, but if there are many different, if there are, let us say, like 100 plus users for any site which you are accessing, or if there are let us say 1,000 different users, or if you have more number of users, so what would actually happen is the history of transactions or history of users will be arrived at. Let us say if there are 100 users accessing a site every day on an average, then that count will be usually picked up as this particular count. So it actually depends on how many users are generally accessing a site or how many are actually using your services. So in general, if we go for any of the big shopping sites, these numbers will be more high. The reason why we want to keep it high is because it is proportional to, let us say, that particular number is right. That particular number, you add it in both numerator and denominator, right? So it actually gives you a sort of a damping effect wherein it will actually increase when you add it in the numerator, but at the same time you add the same number in the denominator, so it reduces it overall. So it entirely depends on the domain, but it actually depends on the average number of users uh, that a particular site is getting, or the particular number of users who are actually viewing it. So it's based on the transactions, Kannan. So here, because of a simple data set, I picked it up as pi. But even if I can go for a different number and can still get maybe around the same values, we can play around with the values.
Yeah, thank you.
Ramesh Babu, just one question. If you look at if you look at this damp mean method, yeah, the user who gave a rating of 5, because he was the only person who rated that particular movie, you scaled his rating down to 3.77, and that's fair. Okay, in
Yeah.
fact, it might even be a little too kind to him, but that's fine. I mean, you have to scale it down. But there are users who have rated a particular movie as 1, 2, 1. So no user has rated the movie above 2. Okay, mostly they've rated the movie below 2. But
Mm.
their rating has been scaled up to 2.7, which means their rating has kind of gone up because of the system. In reality, none of the users who rated this would have had a rating experience of close to 2.7. So actually, the particular movie is being shown as better than what the users are experiencing it to be.
Yeah. So damped mean actually works in two ways. One is if you see this specific movie, right, they've got a rating of 4.25, correct? We have scaled it down to 3.85, right? Even though this movie, let us say in a scale of 1 to 5, if you consider, and if let us say 5 is the highest, then this is a very good movie. But when you use a damped mean, you are actually damping it down to 3.85 to just to keep it not too high, because as and when the number of users keep increasing, we want to keep increasing the average. But it also works in the other way. If the movie rating is so very less, right, for 3 users, we are actually extrapolating it to more number of users by means of a damped mean recommender system, in the sense that if there are same number of users have watched all the 3 movies, what could be the rating is what we are trying to arrive at. So it works in both the ways. One, it actually brings down the highly rated movies to less number of movies rated, less rated movie, and it actually also increases the ratings of the lower rated movie, because we are trying to keep it as a minimum base scale. Let us say we want to keep it as a minimum base scale of 2.5 is an average rating that any movie should get at the first instance. Then it will actually, the base of it, itself will start increasing. It will actually start counting only from 2.5. So that's why you see the number, even though it is 1.33 here, it gets scaled up to 2.7, because we are just trying to shift the base to a specific, because we all assume that the moment a movie has come, it will have an average rating of probably 2.5 or 3, how much ever we want to decide. So here we are deciding that every movie which comes has an average rating of 3.53, and in that base scale we are actually trying to compare the movies. That is why you are actually seeing this particular movie has got increased to 2.7, right? But I understand, because it will actually scale down the highest average movies as well, and it will scale up the lowest average movies because of this average that we are getting and using it as a part of damped mean, because it is trying to bring it to a scale of average around 3.53. You got it?
Thanks. Clear.
Okay. So this is as I said, this is a damped mean recommender system, mainly to provide you an advantage of bringing all the movies or all the products to a same scale. And this is an easy to use algorithm and fairly simple to understand, and can be used at any point of time to derive the most popular ones. And as we said, we have used this term damping in our physics specifically, right, just to actually damp the amplitude of the oscillations so as to keep it within a range. So even it specifies this, it also performs the same case here, wherein it's trying to keep the ratings within a specific range so that all movies or all products get a fair chance. Now, in terms of code demo, we have implemented this fairly simple by means of a normal Python program. I'll just briefly show you that. I have used the same data set which we have seen now. Just give a moment. Okay, so we haven't used any fancy algorithms because it's a simple average based recommendation. So I have read the movies data set. These are the current specific user IDs, the movies, the ratings. I have read the tables, and here we have got the mean simple average rating for all the movies. You see there are around 2500 rows, which means that 2500 different movies are there, which has got its own simple rating. Now in the next few steps, I am implementing the same what I have shown in the Excel in terms of adding it up, then using this damped mean, then grouping it in terms of movie IDs, getting the count, adding the count factor, and just summarizing it in terms of tables, finally merging it and getting a damped mean, and I'm showing the difference for each of the movies, how it actually has damped. So this implementation is available in the GitHub and the specific link which I will share. So it's a fairly simple, as I said, it's no recommender fancy algorithm is required. We can just use our normal Python libraries to implement this. Okay. So coming back, we are actually, as I said, our non-personal recommendation is split into aggregated opinion approach and product association recommender. Now, what I showed you is an algorithm to implement aggregated opinion approach. In fact, there are other algorithms as well, but this is one fairly simple which we can use. The other classification is product association recommender. So product association recommender is a little bit more detailed in terms of associating the two different products. For instance, if I am buying this particular product, or if I am watching this specific movie, what is the next movie or what is the next product that I'm going to buy or watch, right? That is how the recommenders, the product association recommenders, are going to associate between two different products or services. So in terms of retail, if you are talking about product association, it is nothing but what products frequently found together in the cart. In the sense, there are a number of users who go and shop in the specific site or in a specific store. But there could be certain combinations which frequently occur. For instance, many people, if they are buying milk, they might buy cheese along with it, or they might buy a butter along with it. This is like a most frequently found items in a specific cart, irrespective of the users, right? So our association actually tries to figure out what association rule tries to figure out what is the association between two different products in a given data set or a given shopping cart. Now, there is one funda which we all need to understand actually in order to make it very clear. I think these are certain statistical terms which we always use, which is correlation, association, causation, right? But this is a very important principle, which is correlation implies association, but not causation. Conversely, causation implies association, but not correlation, right? We might have used this interchangeably, though in statistical terms, all these mean totally different things. Let me explain you with an example here, right? Let us say if the day is, or if the weather of the day is dry, hot, and sunny, right? Certain set of people might eat more ice creams. The ice cream sales would definitely increase, and more people might get sunburn as well because the temperature is very high as it is sunny. Now, is it possible to say that the ice cream sales is increasing because people are getting sunburn? There is no causation relation between these two, because one is not causing each other, but there is definitely a correlation between these two, because if the sunburn also increases that day, the ice cream sales also would increase that day. You might be able to correlate these two, that if this is increasing, this is also increasing, but you may not be able to establish a causal relation. What is exactly the cause for these two happening is because of the sunny weather on that specific day, right? So this is the difference between causation and correlation. Similarly, we have another term called association. Our whole recommender approaches works for non-personal recommendation works in terms of association. as far as product association recommenders are considered. So what exactly is association is nothing but association is an relation between two variables. That's it. It doesn't give any other information. For instance, if you're able to give information about one variable, it may give an information about other variable. That's it. You may not be able to establish a correlation between those two. For instance, this is an association relation, right? You cannot say this is correlated because it keeps reducing, then it keeps increasing. But in a way, this variable is associated with another variable. That's the only thing information that we are able to get it. Whereas in this picture, it's not associated because a specific variable is lying constant irrespective of other values. But here you can definitely see a correlation relation because you can see an increasing trend. So if you consider this as x-axis, this is y-axis, as if this increases, this also increases. So there is a correlation relation. So that's what this principle generally says. Association is a very general relation. You might be able to get information about one variable from another variable, but you may not be able to actually correlate it. But correlation is more specific. For instance, you may be able to correlate the two variables. If one is increasing, the other also follows the same trend, or decreasing, vice versa. In terms of causal relation, this between sun and ice cream is a causal relation. Sun and sunburn is a causal relation. And co-occurrence is another term, which means that the terms co-occur or occur within each interval. For instance, as I said, you might buy milk and butter together. So if you consider these two are two different events, then they co-occur with each other. So that is what it means. So co-occurrence is a different kind of relation wherein one or more events co-occur within a specific time interval. So what we are going to see in the next few slides are what are the different association relations and how the association relation actually helps in recommendations. Okay, let me quickly. Okay. So certain examples of product associations which we all would have encountered during our interactions or during our purchases are the featured recommendations and recently viewed suggestions, right? These are very generic ones which will be displayed to the user, and this is based on association. You might have also seen when you purchase a phone, it might suggest you a bundle, like you can buy a phone along with the phone case or an adapter. This is called bundle. So bundle relation works on the basis of product association. Cross category related products is nothing but the recommender engine recommends you a product which is not related to the product that you are buying. For instance, if you are buying a dress, instead of if you are buying a shirt, instead of recommending you a pant or a trouser, it might recommend you a shoes, right? Or it might recommend you a books based on your style. So these are cross category. Those all belong to a different category, but still it does recommend based on the associations. Frequently viewed together based on the history of related views. Then you might have also seen customer who bought this also bought that. It's again based on the purchases made by the customers, and all this works entirely on the basis of product association. Now, how do we come up with this product association, or how do we arrive at product association rules? So briefly, we are going to talk about two different algorithms as a part of product association, that is Bayes theorem and the other one is a priori. Now, we would have all seen or used Bayes theorem in our for some of other examples, for some of other problems. But the Bayes theorem can also be used as an association rule recommender engine. Okay, so Bayes theorem is nothing but it describes the probability of an event based on the prior knowledge which is related to the event. It is actually the Bayes equation is actually arrived as an outcome of conditional probability, right? For instance, these are the conditional probability equations. Probability of A given B is probability of A comma B by probability of B, which is occurrence of A and B by probability of B. and you can get the probability of A and B, which is the occurrence of A and B by means of conditional probability of A given B multiplied with probability of B. Let us say A and B are two different events. So same is the case for probability of B by A. By this way, you will be able to actually arrive at this specific Bayes equation, which is a very common equation, right? Now, what exactly do we mean by probability of A given B? If you take into a real-time example, let us say B is an event of purchasing milk. A could be an event of purchasing bread, right? So what is the probability that you would purchase bread given that you have purchased milk? Or probability of purchasing butter given that you have purchased bread, or vice versa, probability of buying milk given the probability of buying bread. So this is a sort of a conditional probability that can be arrived at by using Bayes or conditional probability. So what we are going to do is we are going to do a simple exercise of how we are actually using Bayes theorem to arrive at the recommendation for movies. Let us say the scenario is you log into Netflix and you start watching or you start browsing about a specific movie, right? Now, given that you have started watching or liking a specific movie, the recommender system needs to know what is the next movie to watch, right? At this point of time, it doesn't know anything about you apart from only one thing, that is you started watching a movie. Now, how does it do it? It applies the Bayes theorem or conditional probability indirectly. So what it calculates is it calculates the affinity score between the movies. Okay, and how is the affinity score computed? Affinity score is nothing but it computes on the basis of common viewers between movie M1 and M2 by distinct viewers of M1. Let me give you a simple example.
Yeah, Ramesh, this seems like the classic Bayes formula, isn't it?
Yes, yes, Vivek. It's a classic Bayes.
Okay. So now instead of calling probability, we are calling it affinity score.
That's right. Yeah, that's right, Vivek.
Okay.
We're just calling this an affinity score. So let us say M1 is watched by users 1, 2, and 3. M1 is nothing but movie 1. M2 movie 2 is watched by user 2 and 4. This is based on the historical transactions. Now, how do we get an affinity score? Is what are the common set of users here? User 2 and user 2 has watched both. So 1 divided by what is the affinity score for M2 and M1? Given that user has started watching M1 is what are the distinct users of M1, which is 3 users have watched. So it's 1 by 3. So this is how we compute the affinity score. And as we discussed, it is a basic conditional probability which can still work good to derive you the affinity score that can be used as a basis to recommend the movies, what next to watch or what product to buy next. So let me quickly show you an example. Okay, so here we have used the same movie data set, and what we have done is we have actually merged two different data sets and brought it in this format, wherein these are the different user IDs, these are the movie IDs. What it means is that the movie 1 is watched by so many different users, right? Same for different users. We just group the data set in terms of the movie IDs. These are the movie names. We figure out the different movies. As we said, what we do is we actually find out what we do is we get the distinct movie sets. So for our reference, I just picked up only 11 different movies, and what I did is given that the user has started watching movie 1 or 2, whatever is our input, let us say the user has watched movie 2, what is the next movie that the system can recommend? It runs this conditional probability, or it computes the affinity scores, right? And it has computed the affinity score as you see here, right? The affinity score between 2 and 1. This is how we have to read it: 2 and 3, 2 and 4, 5, 6, 7, 8, 10, 11. Because we have selected only a subset of original movies coming like this, right? So we can actually apply a filter criteria after we have got this affinity, computed the affinity score. And let us say I have applied a filters criteria of only recommend me the movies which are greater than 0.3. Then it will only recommend you the movies which are greater than 0.3 affinity score, which is 1, 6, and 10. So the system would go ahead and recommend you one of these 3 movies for you to watch, provided you have watched movie 2. Similarly, we can get affinity score between any 2 movies, and based on the affinity score, the higher the affinity score, the system will recommend the specific movie. For instance, though I have applied a filter criteria here 0.3 and got 3 different movies, I can see the highest one affinity score is 1, which is 0.86. So I will go ahead and recommend 0.1, sorry, this movie ID 1 to watch. It's nothing but it is based on the affinity between the users who have watched the same set of movies. Okay, so I hope this is clear. It is very simple. It's simply on the basis of the conditional probability and I mean the base 1. Now coming back to the association rule learning, right? In terms of associations, there is a very interesting story which has been repeatedly told for last 50 years or so. It is nothing but a beer and diaper story. These two seem to be hardly related, correct? I mean, beer and diaper. What is the relation between those two? But still, one fine evening, it seems a supermarket manager took out all the transactions which were made on that particular week or a particular month, and when he started doing an analysis, he did discover an interesting trend that between 5 and 7 p.m. on every Friday, the consumers who bought beer did buy diapers. So it's hardly something which we would have figured out, right? I mean, with something which we wouldn't have even imagined, that a person's buying beer would also buy diapers. That there is no relation between those two, right? But still, there is some association which the store manager has figured out by means of data mining. So this is a sort of an association rule that we want to discover by mining the data which is there available as a part of our transactions. So this is what is collectively called as association rule learning. Association rule learning is nothing but a rule-based machine learning to discover interesting relationships between the variables in a large database. The rules could be strong, weak, depending on how we want to actually categorize or how we want to associate, but the association rules are something which are derived based on the transactions that people do, and it will actually discover some interesting associations between the different transactions or different items. So in general, the association rules will be in this specific form, that is A given B, something like this. How do we have to read it is, we have to read it in the form of if then. For instance, if this occurs, then that is highly likely this also occurs. If you want to give an example of a quick store, if somebody buys sandwich and cookies together, then there is highly likely that they will buy a drink, a soft drink, right? This is sort of an association rule. So there could be many such association rules that we would discover if we start mining the data of the historical transactions, right? So these sort of rules are what will be discovered by means of association rules, and the algorithms which facilitate this is nothing but association rule learning algorithms. An interesting one of the very specific fields which employ association rules is market basket analysis. We have to, I just the acronym is MBA. It's nothing but market basket analysis. Market basket analysis is a term which is specifically applied to the retail stores where people buy items in large quantities day in and day out. Okay, so it is a type of an association rule learning, and it tries to establish the relationships or find the patterns across the different purchases. There are certain common terms used in market basket analysis. So these are the terms that we have to just understand that. First thing is item set. Item set is nothing but a collection of items purchased by a customer. It could be a sandwich, burger, or it could be a sandwich and burger. It could be a simple transaction made by the customer. Antecedent, consequent, right? I'm just going back to this rule. If you purchase this, then there is highly likely that you can purchase this, right? This is the rule we got. So this is the antecedent, that is the sign. Whatever comes in the left side of this rule is antecedent, and whatever comes in the right side is consequent. And there are three different terms that we actually evaluate for a specific rule to actually say whether or not we need to use these rules, because there is high chance that there could be hundreds of rules that we would get by mining a specific data set, but it is not necessary that we need to pick up or use all the rules, because we always go by specific threshold. For instance, a support should be greater than a minimum support. Similarly for confidence and lift. So I will show you what are these different terms. I will explain you with an example, but all we need to remember is for any rule, for us to use any rule to make recommendations, it actually looks for, it computes the support for the rule, confidence for the rule. It would also compute lift for the rule. And only if it satisfies the criteria, if it is greater than support, greater than confidence, or greater than lift, what we desire, the rule will be implemented, else the rules will be ignored. So that is the key thing about the association rules. Now, to explain what support, confidence, and lift means, we'll just go back to my example. Okay, let's take a simple data set. Let us say there are some total different, there are a total of 1,000 transactions being made, and out of 1,000 transactions, probably we have 100 transactions which has got ketchup. There are 100 transactions which has got burger, right? Let's say you are in a fast food and there are that you are recording the transactions. You would realize that there are like some 1,000 transactions which are made, out of which 100 transactions have got only ketchup, 150 transactions have got burger, and there are 50 transactions which have got both burger and ketchup, right? Now, how do we compute the support, confidence, and lift for this specific for a specific transaction? Now, support is nothing but let us say we are trying to figure out support for ketchup, right? You are trying to figure out support for ketchup. What you will do is you will actually get the total number of transactions which has ketchup in it divided by total number of transactions. For instance, here we have 100 transactions which has ketchup out of 1,000 transactions. So the support is 10%. Similarly, you can compute for burger as well, which will be 150 by 1,000, and you will arrive at a percentage. So, and you are interested in a specific rule, that is, let us say if people are buying burger, what is more likely that people will buy ketchup, right? So it's nothing but a simple formula: transactions that has got both burger and ketchup, which is this one, divided by transactions that has got only burger. So using that specific formula, we arrive at 50 divided by 150, which is 33%. So which means that you are 33% confident that if people buy burger, then there is a chance that the same people will buy ketchup. And we also associate one more term in addition to confidence, which is lift. Lift is nothing but confidence by support, which is 33% divided by the support for ketchup, which is 3.33. So why do we compute confidence and lift? Support is actually to tell you how many percentage of transactions has actually arrived, is present. For instance, we don't want to actually associate or do rules for items which are appearing very rarely or frequently. That is the reason why we pick up support. And once we get confidence, once we understand confidence in the sense that if say X number of people buy, if say 100 people buy ketchup, I want to be confident how much percentage of people will buy burger as well. Sorry, if let's say 100 people buy burger, I want to know with confidence how many people will actually buy ketchup. That is why we are using confidence to understand how many transactions who buy ketchup. How many people who buy ketchup will still buy burger. How many people who buy burger will still buy ketchup. But lift is an additional term that you can use in addition to confidence to actually figure out whether this confidence is appearing as a statistical one or it is purely random. For instance, if there is any popular item, right? For instance, drinks might go with anything. Either it might go with burger or it might go with ketchups. So in that case, if you compute confidence for burger given drinks or ketchup given drinks or drinks given burger or drinks given ketchup, there will be high confidence because drink could be a popular item that will be present that might go with all the different items. So in order for you to do an extra validation, you also go ahead with the lift, because lift will actually take into consideration the statistical independence, which is arrived by this particular formula. Lift is nothing but a total support of both X and Y occurring divided by, given if they are independently occurring, right, X and Y, then what is the lift that you are getting? For instance, if X and Y, if you want to compute this specific rule, Y given X, then you compute if X and Y are independent, then this is the support that you will get, or this is the number of transactions that we will make. But however, if they have any association, then this is the number of transactions that you will get. So if a lift greater than 1, which means that if the combined transactions of X and Y are greater than individual transactions of X and Y, then you can actually very well go ahead and recommend this particular rule. But if the combined transactions of X and Y, which means support of X comma Y is less than support of X into support of Y, which means that if they are occurring independently, if they occur more compared with if they are occurring together, then you may not actually recommend a lift. For instance, if lift is less than 1 or greater than 1, or it could be equal to 1, there are 3 different possibilities. If it is less than 1, then you can say that there is a negative correlation, which means there is highly likely that negative correlation, there is highly likely that you will not purchase an item associated with it. Whereas if it is lift is greater than 1, then it is high correlation that you will purchase it. The 2 items are related and you can go ahead and recommend. And if lift is 1, you may not be able to make any inference. So lift and confidence are used to actually arrive at whether or not you can go ahead and recommend the rules for your future recommendations. Now,
Rameshbabu, sorry to interrupt.
Sorry, yeah,
Hello.
sorry.
Yeah, just one very brief question.
Mhm.
When you in the Excel sheet, when you're saying -1, 1, and less than 1, greater than 1, and 1, are you implying correlation or are you implying association?
Yeah, I am actually implying association.
Okay, thanks. I just wanted to clarify that. Thanks.
Yeah, okay. So I will just term the terms because it's actually an association. We are not talking here about correlation. So negative association, it is positive association. So I'll just there is an algorithm specifically which is commonly used to implement this association rules learning, which is called as a priori algorithm. The a priori algorithm is an algorithm which is which is actually used for frequent item set mining. So as I said, we actually want to implement or derive the rules based on the frequent item sets, which I explained you by stating that anything less than support we should not consider, right? Once we get a frequent item sets, we were trying to establish the rules from the frequent item sets using certain steps, and that is there are certain steps involved in for a priori algorithm, and this is what those steps. For instance, step number 1, it will calculate the number of support of the item sets, and then it will generate the candidate set. And the step number 2, it will prune the candidate set by eliminating the items with support less than the given threshold. And step number 3, it will generate the support, confidence, and lift for the associations. And step number 4, it will filter the association based on the business needs. So I'll just explain these steps in terms of an example, so it is very clear. Let us say, so actually in real time, there will be a huge number of transactions that we need to pick up for analysis. But here, I'm just keeping it very simple. For instance, let us say there are only 4 different transactions, and these are the different items. That is item number 1, 2, 3, and 4. There are 4 different items in a store, and in a single first transaction, in the first transaction, these 4 items are bought. In the second transactions, item number 2 and 3 are bought. In the third transactions, 3 and 4 are bought, and in the fourth transaction, 2, 3, 4 are bought. So these are 4 different transactions that we are going to use to mine the association rules. Okay? So as I said, if we are using an a priori algorithm, as our first step, we need to actually set up what we want to set up as a threshold for all these factors. So we want to actually set up, we want to actually set up this thresholds for support as 3. We want to set up the confidence as 80%. We want to set a lift as greater than 1. So we want to actually pick up the rules which are only falling under these criteria. It's up to us to change, but it is always better to keep confidence and lift higher so that we get some good set of rules. Now the support, you will actually set this number based on the average transaction size that is happening. Here I just kept it as 3. Now as a step 1, it actually needs to generate the different item sets. When I say different item sets, it actually combines the different transactions based on different transactions based on the items. So as a step 1, it will actually do an one item set, in the sense there are 4 different unique items, right? So these are the items 1, 2, 3, 4, and when we compute the support for each of these items, in the sense that how many times these items are appearing. Item number 1 appear only once, right? And item number 2 appear thrice, as marked here, and item number 3 appears 4 times. Item number 4 appears 3 times. Now from this, we actually navigate to 2 item set. From this, we navigate to 3 item sets. I will just, because the algorithm is all about increase starting from a minimal item set to maximal item sets that is possible. So you can actually go for 1, 2, 3, 4 also, right? But we will show you why we are not going towards that. Now we have set a support as 3, correct? What it means is any items, anything which is less than 3, we may need to take it off. So we figured out that item set 1 is occurring only once. So I'm just striking it off, whereas all others meet this criteria. I mean, it's greater than or equal to 3. So we are going to the next transaction set, which is 2 item set. So I am not considering 1 at all now. I am considering only 2, 3, 4. Within 2, 3, 4, what are the different combinations possible, which is 2, 3, 2, 4, 3, 4, correct? Now I am trying to get a support for all these things. So how many times 2, 3 has occurred? So it has occurred once here, it has occurred twice here, it has occurred thrice here. So I'm entering that support. Similarly for 2, 4, similarly for 3, 4. So these are the support items. Now again, applying the same rule, this is taken off. This combination will not come. Now we are left with only 2, 3 and 3, 4, right? So between 2, 3 and 3, 4, what is the best combination? It is not possible to make 1, 2, 3, 4 combination, correct? Even though we have 4 item sets available, because this is not a frequent item set since 1 is already gone. So we are making this combination 2, 3, 4. Remember one thing, in a priori, it doesn't take sequence into consideration. So whether it is 2, 3, 4, 3, 4, 2, 4, 3, 2, it still considers all as co-occurring with each other and just come up with an association rule. So now taking 2, 3, 4 into consideration, we see that it is occurring once here, it is occurring twice here. So it has support of 2, which is less than 3. I'm striking it off. So finally, we are left with 2, 2, 3, 3, 4. And these are individual item sets. We will not be able to make any rules just by having only one item set, right? So we need a minimum 2 item set for making rule, in the sense that we want to see whether 2 implies 3 or 2, 3 implies 4 or 3 implies 4 or 4 implies 3 or 4, 3 implies 2. So we want to have minimum of 2 item sets so that we can make some association rules. Now the step number 2 is computing the confidence. Step number 3 will be computing the lift, and step number 4 will be arriving at the rules. Now in terms of computing the confidence, right, I am taking 2, 3 and 4. 2, 3 and 3, 4. So between 2 and 3, it can either go this way, that is 2, 3, 2, 3, or 3, 2, right? So it can go either way. So but the meaning of these two are different, because this is 2, 3 given 2, and this is 2 given 3. So I want to find the association. I want to see whether the association rule holds good for the different item sets. So I'm considering as 2, 3, 3, 2. Similarly for 3, 4 also, I'm doing as 3, 4 and 4, 3. Right, and I'm trying to compute the confidence. First thing is I'm just computing the support of these. So I get the support numbers. Then I'm computing the confidence by the formula, which is support of this specific item set given by the number of occurrence of 2. For instance, if it is 2, 3 given 2, if you want to find out this particular rule, then you have to see what is the combination of 2, 3 occurrence given by divided by the number of transactions which has only got 2, which goes by this particular formula. This particular formula, frequency of occurrence of 2, 3 divided by frequency of 2. So I compute the confidence. I compute the confidence in a similar manner for all. So I arrive at the confidence of 100% for this, 75, 75, and 100%. Now, since I have set the confidence as 80%, anything greater than 75%, I just strike it off. I just go with 2 and 3. So these are the possible 2 association rules. I'm 100% confident that whenever you are buying item number 2, you will buy 3. Whenever you are buying item 4, you will always buy 3. So that is the interpretation that we can make at the end of this confidence computation. Then we can go ahead and apply lift. Lift is again based on the specific formula, which is support by individual supports. Now if I use that, I'm getting a lesser value. Now here I'm getting a lesser value mainly because the transaction set is limited in size. Usually for limited data sets, we can just go ahead only with confidence, and for huge data set, you can go ahead with it. But still, I computed lift here. Lift here shows a lesser than 1 value, so I would definitely not go and pick up these rules. But since the confidence is 100%, you can still go ahead and recommend the rules. It's up to us. But since the data set size is limited, we are not able to get enough association rules if we consider lift as well. So this is exactly what is done by the a priori algorithm. It just first step, it generates the candidates, then it eliminates based on the supports, then it generates the supports, confidence, and lift. Then it will filter out the association rules based on the needs. We can set up the association rules. For instance, you can actually go ahead and set up the confidence as 60% as well. If you do that, you might actually pick up all the rules, and then you can use these rules for further recommendation. So it's based on the business needs is what you have to decide, but higher the confidence and lift, better it is for you to recommend the association rules. So we have actually specific library called a priori, which can be used to actually come up with this association rules. That's what we have used here. For instance, I have picked up a store data set which has got transactions for the entire week. You can see around some 7,500 transactions have been made, and the a priori algorithm, what it requires is it recommends you to requires your input in the form of list of lists. So I convert the data frame into, I remove all these NaN values, and I keep only the individual transactions, the valid transactions, and then I convert it into lists. And we have an algorithm, I mean, we have a library available ready-made, which is a priori algorithm, for which you need to pass the records, and then you need to pass the minimum support, the minimum confidence, and the minimum lift, and the minimal length. So accordingly, it will actually come up with a different set of association rules, which can be derived as an output here. And I just printed it for better reference here. Now you can actually see that based on this specific transactions that we have made, actually it says that for this specific rule, that is, given that a customer will buy chicken, that he has bought light cream, his support is this much, confidence is this much, and the lift is 4.84. And given that the customer will buy this escalope, given that he or she has bought mushroom cream sauce, is this. So it gives you so many different rules, right, based on different combinations, and you can use this rules as a basis to do next recommendations. Or alternatively, what people would do is this can be used for marketing campaigns as well. For instance, if a person has purchased only pasta, right, the store owner might actually run a marketing campaign so that the person can actually purchase shrimp, because he or she might be interested in shrimp, given that the association rules says that more people purchase pasta, more people buy shrimp. So that is the kind of inference that they are getting. So they can run a marketing campaign targeted to this specific group so that they can buy shrimp. So this can be used for different purposes, how we want to, but in general, the a priori algorithm is used for product association recommendation. Just to summarize, what we saw in this session is a non-personal recommendation that can be recommended individually, or it can be recommended at the group, at a semi-group level, based on the product associations or the opinion aggregations. And in general, the association rules are based on what was bought frequently, so we can mostly classify it under frequently bought together recommendations. And we did see that affinity score computed as a conditional probability or Bayes theorem is useful in terms of making recommendations for movie data sets. And in terms of market basket analysis, for which we applied a priori algorithm, there are different use cases which are used, and more, and they can be few of the use cases are product placement. For instance, how you want to place your products, like do you want to place olive oil next to ground beef and milk, or do you want to place spaghetti along with ground beef and shrimp? So you can use it for product placements, and in the physical store you can use it as a shelf arrangements where you can keep the related products in the nearby shelves. You can use it for upsell, cross-sell, or bundling opportunities. The moment a person buys spaghetti, probably you can recommend spaghetti, herb and pepper, and ground beef. And you can use it as a customer retention strategy as well, because the moment you know that the customer is more interested in purchasing specific items, or if you link it to a specific services offered by a telecom company, these could be specific services offered by the telecom company, and these could be services which customers would be interested in. So you can actually cross sell this specific service, or you can actually recommend this as an alternative to this service, or you can use this to target specific schemes to the customers so that they remain with the company. So it's also used as a basis for customer retention. So the application is not only with the e-com specific sites where shopping is made, but it's widely used across all the industries such as telecom, banking, to market the financial products, to detect the frauds, because on seeing the co-occurrence of patterns, and most commonly in stores sites for actually recommending the items. All these for all these preparations, we have made references to the different sites, which I have given the details here, and that's all. So this is a brief about non-personal recommendations, which is further a stepping stone for personal recommendations. Do you have any questions?
Okay, audience, any final questions? So this is the beginning of our, recommender system series. So here we have some very important historical or legacy algorithms used in recommenders so far. And increasingly in this course series, we'll be looking at more and more sophisticated deep learning based recommenders. But it's important to understand the legacy, statistical models which existed. They still hold value for business applications. Audience, any final questions? Okay, so I guess Ramesh, that's about it. Thanks for an excellent session. Thank you, audience, for joining.
Thank you, Vivek. I'm stopping the recording.